Okay, we continue with our lecture for the bioreactor engineering. Today I'm gonna talk about how we do the heat transfer inside the bioreactor. So sometimes we need to remove the heat from our system to cool it down because we want to protect our products to be like it's unnecessarily scenario to be occur. So today I will cover the heat transfer theory. Is about equipment, mechanism, conduction, convection, and other example of we use to calculate the temperature change in the bioreactor. So let's begin. So this is how the heat transfer equipment is inside the bioreactor. So first one, the A is jacket vessel. So it's like you put on the jacket and then you are working fluid inside like this. External coil is like this. Okay, you pass your products to here, and then this one is internal coil. This one is external. So this one is the gray one is your products. This one is internal coil, helicoid, and this one is installed inside the coil, and this coil is function as the heat transfer equipment and also the buffer of your system. And sometimes we use other exchanger to transfer the heat. This one is called heat exchanger. So you just pump out your products and then exchange and then you feed it back to your system. This is how the heat transfer equipment look like. So we can come back is later on and then we look at later. And this is how we want to keep our fermenter temperature. So we want to keep the temperature is constant because we want to protect our product degradation, for example. And this is how the cooling temperature is changed. So this one is inlet cooling point, and then this one is outlet. So the temperature just change a little bit to maintain the temperature inside the bioreactor. Okay, this is distance from the inlet, for example. And this is like this configuration. This most common use heat transfer heat exchanger. This one is called double pipe heat exchanger. So you have two pipe. One is inlet, one is outlet, and this one is in the inner tube. So it's your product. So this one is outside. So it's called, this one is like counter current. So you have this direction and this direction. Okay, and the other one is shell and tube. This is more common for chemical engineering. You have the shell side like this. You throw it in and then out. And you have your this one is shell side. This small thing is called tube. This one is shell and tube. So you have very small tube inside. You have inlet and outlet, and you have other thing as well like counter current. So your flow is on the same direction. And you have another one is counter current is opposite direction. We can come back later on for how to calculate the area inside. So we have three kind of heat transfer. The first one is conduction. Conduction is caused by vibration of energy between molecules and is related to the metal. So you have your fermenter, you have the wall. The wall is most of the time is made of metal, stainless steel, for example, And the second mechanism is convection. Convection is movement in macroscopic level. This one is related to very small tiny things in terms of molecule. We have forced convection, we just force it to occur, and we have natural convection as well, which is it occur naturally inside the fluid. And the forced convection require external force such as stirrer. You have stirrer, we have different turbine, for example, and propeller, pump, okay, something like that. And the last mode of heat transfer is radiation. Radiation occur at a very high temperature, which normally we don't see in the bioreactor system. So, and then this kind of mechanism will not mention further for our lecture. So we must consider only conduction and convection for later on. But for the radiation is, like I said before, is a required form of wave and then occur at very high temperature. So we won't mention it later on. For the conduction, we require the Fourier laws. Q is heat, K is thermal conductivity, and A is area. And this is one is your driving force. Again, for the heat transfer, the driving force is the temperature change. So we have from the book, so we have different kind of different unit of thermal conductivity. So aluminum, for example, iron, and this one is related to the solid wall, as I mentioned before. Yes, and then we can look at the calculation later on. This is how, if you pass 3 different kind of metal, 1, 2, 3, and then you have this temperature change. So delta T is delta T1, delta T2, delta T3. The total Q is delta T, which is this one, and resistance R1, R2, and R3. And then this is how R1 and R2 and R3 is calculated. K is again thermal conductivity. Different kind of metal have different kind of conductivity. And then B is the the distance. A is their area. Area is the total, the surface area that the heat transfer. This is how we use the conduction. And normally with different fluid, so we use this kind of thing for calculate. This is question 8.19. Q heat, U is overall heat transfer coefficient, A is the area, and then delta T is hot and cold. It's between the hot and cold side. Okay. And the basic calculation for this one, if Q and U and D are known, this equation known as calculate. Area is more important for heat exchanger design. The surface area configuration is we can calculate their cost later on. And then this one is more very important, the heat transfer coefficient, because we can use the suitable heat exchanger for our system. And then this is we will continue on the example 9.1 later on. And this one, shell type heat exchanger coefficient. So this one basically is a single pass shell and tube heat exchanger. This one, shell and tube, and single pass as well, and used to heat. So you want to increase the temperature. Dilute solution of large scale protein chromatography. For this is your process. Salt solution plus 2 parallel tube, 42 tube. You have 42 tube inside the heat exchanger at total volume of this rate 25.5 cubic meter per hour. Internal diameter of the tube is 1. This a small tube is 1.5 centimeter. The tube length is 4 meter. It's quite long. Viscosity is like the same viscosity of the water, so it's very dilute. The density, okay, again is slightly heavier than water. Average heat capacity Cp, mCp delta T, this that just your temperature change. This is your K, conductivity is this one. And then we want to calculate the U, heat transfer coefficient, for this example. And we have a look. So we have the total area 42 number of tube, and then cross-sectional area of this tube, and then we have this area in terms of meter square. So we have 42, and then each tube has this surface area, and we calculate the velocity, volumetric flow rate, and then this is that one that you calculate, and to change the unit to meter per second. For this one, this U, you calculate the Reynolds number of this one is turbulence is turbulence, and this is Prandtl number, okay, is from equation 9.28 and 9.30. This one, okay, we have a look this one. Okay, this is Reynolds number from the pipe. This is impeller Reynolds number, and this is Prandtl number, Cp, that one that's given to you, mu and K. Okay, and we continue later on, and this one, and then we calculate the Nusselt number, and for the Nusselt number we can calculate the heat transfer coefficient. So you choose your heat exchanger to have this kind of heat transfer coefficient. It has 4,335 watt per square meter and per degree Celsius. This one, this is from your calculation. This is the problem. So this one is heat transfer coefficient, the H for the Nusselt number. This one, Nusselt number. Okay. Again, this is heat transfer coefficient for this one, and then the second one is what? Calculate the heat transfer coefficient again, but it's different. This one is stir fermenter. This stirrer has helicoid, for helicoid, internal helicoid, which is this one. Internal helicoid is this one, the the C, internal helicoid, this one. And okay, and this is the stirrer RPM, 60 RPM revolution per minute. The fermentation broth, okay, this is broth, the liquid inside the fermentation. This is viscosity, density, and this Cp, Nusselt for the Prandtl number, and this is K. Neglect the velocity change. Okay, we just use the same. We calculate the heat transfer. Again, we use the Reynolds number, but this one is impeller Reynolds number. This one, impeller Reynolds number is this one. Okay, Ni, Di, rho, and mu. Okay, continue, and then Prandtl number is this one. And you calculate the Nusselt number, and then from the Nusselt number we calculate the H heat transfer coefficient is 1.55 kilowatt per square meter and per degrees Celsius. And if you cannot catch up with the calculation, you just pause the video and then have a look on this equation again. This one is mu B and mu water is the same, okay? Because sometimes the the fermentation broth had the same property as the water because it's a very diluted. Okay, for example, like that. This one is heat exchanger again. Hot, fresh, free, sterile. Sterile means very clean. Nutrient medium is cool. So we use double pipe heat exchanger before use in. So we just exchange the temperature before we use it. Medium leave the sterile at 100 degrees Celsius. Enter so it's quite hot after you are sterilize things. The heat exchanger at the flow rate of this one. Desired outlet temperature is from 100 to 30 degrees Celsius because we can use it later on. Heat from the medium is used to raise the temperature of this one. Cooling water, this one, steady state. Again, we assume the nutrient has the property of water. The density, the viscosity is the same. First, calculate the heat required, and the second one is we calculate the cooling water outlet heat cooling water. Okay, this is hot, this is cold, so the density is the same. This one. You can pause the video and then have a look at later on. This is hot. Hot is this one. This one, this hot one. This is a cool side, cooling water. This is hot side, which is the medium. The medium. So basically, you just change from volumetric flow rate, this one, to the mass flow rate. So this hot side and then this cold side. Okay. And the heat exchanger that we used in this calculation is this one. Double pipe heat exchanger. And again, so you continue working on it. And CP, okay, this one is CP of water. So the hot and the cold is the same. This one, this is the CP. The CP. And again, this is Q. Q is M. This one is for hot. Hot is the temperature reduced from 100 to 30. This is your CP. This is hot side. This first one, heat, is mCp delta T, kilojoule per second. Okay, this one is kilowatt, for example. And the cold side, this one, the temperature from 15, so it's a bit increased. This Q is the same, so we assume that there are no heat loss. mCp delta T. The exit temperature is 43 degrees Celsius from this equation. mCp delta T again, mCp delta T again. Oh, it's the temperature change is quite high, 15 to 43, and then this one is reduced from 100 to 30 degrees Celsius. Okay, this is how we summarize the relationship equation for the fermenter cooling. So you have this property from your system. Fermentation fluid, fermentation broth is the same. Cooling water, and then we use to calculate the hot and cold side heat transfer coefficient. Overall is this one, fluid, hot, conductivity, cold, and this also and cold. This one is fouling factor, for example, and we put in this one is U, overall heat transfer coefficient. This is area, L, and R and L, for example. The delta T sometimes is from logarithmic mean. It's called logarithmic mean temperature difference. This is heat for the cold side. This is heat for the hot side. Okay, mCp delta T again. Sometimes it has the reaction, for example, phase change, and then you have the stirrer, for example, is a sharp work Okay, this is energy balance from the cold and the hot side. In this case, the hot side is fermentation broth, and the cold side is cooling water. Okay, this is the summary how to do that. And this one, we calculate the cooling coil length in the fermentation design. Fermentation is used antibiotic production. Okay, we want to keep the temperature like this one. The fermentation, we want to keep it constant at some point. In this case, we want to keep it constant at 35 degrees Celsius after considering the oxygen demand of the organism and the heat. Okay, the maximum heat transfer, this Q. The maximum heat transfer, this one is Q, is 550 kilowatt. Cooling water is okay. Enter at 10 degrees Celsius, it's quite cold. Exit temperature is 25, so from 10 to 25. Heat transfer coefficient is estimated by this equation. Okay, this one is H. Let me see, 9.36, which is this one. This one is how shell and tube look like. 36, which one? Okay. Where is 36? 9.36. Okay, it's not so number. Okay, I think it's the H one. Okay, H. Okay, continue. Is H this one, and then in the heat transfer coefficient for cooling water is the proposed helicoid inside the fermentation. So it's inside helicoid diameter of this one 8 centimeter. The pipe wall thickness is 5 millimeter. The thermal decay is this one. Average fouling is this one. So basically you just calculate everything here, okay, from this equation. Okay, what they want to know is what length of the cooling coil is required. What length of the cooling coil is required. Okay, we begin with the temperature difference, which is log mean. Log mean 25. This one, this one, delta T2, delta T1. So we have a look again. To put in the number, delta T log mean is 16.4 degrees Celsius. Okay, log mean for the temperature. This is Q, kilowatt. This one, this is Q. And U from this equation, okay, you put everything here. 9.25, and then you have this number 1, 2, 3, 4 term. And yeah, you can neglect some term. This is total 5 term, but there are some term that is negligible. Okay, no fouling layer. Okay, this one you don't use it. You just have a look at the unit as well. It should be the same. Overall heat transfer coefficient is this one, 1355 watt per meter square per centimeter. Okay, A, Q, U. Okay, you got it. And then this one, this is the area of the helicoid. Okay, total area. And then L is A, R is this one. The total coil is required. Okay, this coil is something like this. You just make it helic to reduce the length. like it, put it more it helix one like this, but you have also tolling from this one, from the area you can calculate. Okay, this is how it look like, something like this. So this is the real things. So it's quite long, but you make it as square, something like that. Okay, and the total length is 105 meter. So this one, okay, and this is how you calculate the things. So you just try to find the area. From the area you find the length. 2 pi r l is area. 2 pi r l is your area, for example. And I have the special problem for this one. So this is how the Helicoid look like. I have the fermentation cooling coil. This one, the fermentation factory is set up to in this city to produce anti-UV compound. Anti-UV compound from newly discovered bacteria stain. Okay, will used to in Bahamas for the country. Import sunscreen lotion achieve. Okay, this is how they describe their problem. Achieve second-hand bioreactor purchased from cash strap from in Cayman Island. Okay, is which is newly cooling coil. So it's similar to this one. Okay, fermentation is carried out at, okay, it's the same as this one, nearly the same. Okay, cooling water is available. Okay, this is from 10 to this one is 15. Okay, and then from 15 to 25. Okay, based on, okay, this is cooling water based on the heat reaction. This is your heat required. This one, overall heat transfer, overall, this one is overall. You don't need to calculate everything. This one is overall already, overall heat transfer coefficient. This one is U. Okay, you don't need to calculate this one. This one is also U. Okay, what is the length required? So your answer is 25. So you can have a look at it and then you work on it. And if you have your problem, we can discuss it later. And this is how it look like. Again, I will take a break a little bit. So far we have momentum, which is Newton law, and Fourier law is we already passed this one, is heat transfer. And then the next part is the driving force is concentration. We use the Fick's law. Okay, and then we will continue on mass transfer operation again for the next lecture. For today, I think it's already enough for the lecture. We will see again in the next lecture. Okay.